Okay, so today we're going to do this kind of conceptual Fatou's lemma problem. Let f of n be a sequence of non-negative integrable functions such that f sub n of x goes to f of x almost everywhere as n goes to infinity. And the key that we see why we want to use Fatou's is this non-negative sequence of non-negative. So that's a condition, right, for Fatou's. Also this lim inf. So this lim inf really keys us in. And remember, what Fatou's tells us is that if we have a sequence of non-negative measurable functions and f of x is equal to the limit as n goes to infinity of f sub n, don't forget the inf, the lim inf, right, of f sub n of x, then we have f dm is less than or equal to the lim inf as n goes to infinity of our f sub n's. And notice basically what this is telling us is that the lim inf pulled outside is going to be greater than or equal to the lim inf of the inside. Okay, so how do we prove that f is integrable? Remember that if f is finite, then it's automatically integrable, or when the integral is finite, that means it's integrable. So we have that given lim inf of f sub n of dm is less than infinity, right? We automatically will have a bound for our integral as well. And since f is the pointwise limit of measurable functions, it's measurable. Its Lebesgue measure is non-negative, and because f is non-negative, infinite. So let's write f is measurable, right? Also, its Lebesgue integral is finite. And then this shows that f is integrable. Cool. So now let's give a counterexample as to why we can't have equality. So why does Fatou's give us greater than or equal to rather than just equal to? Or I shouldn't say just equal to because that's like stricter. Well, let's consider f sub n is equal to our indicator function, n plus 1. And remember, what this indicator function is telling us is that at this point x, we have the function is equal to 1 when x is in this interval, and it's equal to 0 when x is not in this interval. All right, now let's apply Fatou's and see what both of these things are equal to. So the limit as n goes to infinity of r chi of n plus 1. Remember that by definition, this whole thing is just equal to the measure of n comma n plus 1, which is going to equal to 1. So this is the limit as n goes to infinity of 1, which is 1. Okay, well, what about our pointwise limit? We'll see that for our pointwise limit, we have limit as n goes to infinity of, so I guess I should have put a lim inf here, but, oh no, because we're not really directly, we're just trying to, okay, never mind. So when we do the pointwise limit, however, we have limit as n goes to infinity, f sub n of x equals limit as n goes to infinity of our indicator function, right? And notice that as n goes to infinity, eventually we'll be, our x, right, will not be in this interval anymore, because say our x is fixed at this value, right? Maybe for n equals 2, right? X is in here, and we do get that this indicator function is equal to 1. But eventually, as n gets bigger and bigger and bigger, you'll see that this window will pass by x, and our indicator function will equal 0. So this is equal to 0. Okay, is 1 equal to 0? No. So we can't conclude that we can pull the limit in. And we're done.